Hello, we are going to discuss fifth case study. This is penultimate one. We have 6 case studies total. This is the fifth case study. Here again we illustrate a significantly sophisticated application of compliant mechanisms in building a robot that crawls over pipes externally. There are a lot of internal robot crawlers, but this one goes externally, and that is what we will discuss. It is actually a pipe crawling robot. It crawls over a pipe on the outside, that is why it is external, and what it uses is a compliant mechanism, and it uses SMA, that is shape memory alloy actuator. So, in this lecture we understand two things: how to make an external pipe crawling device, and also how to work with shape memory alloy when you are using compliant mechanisms. There are some nuances there. It is not enough to have a smart material like SMA, shape memory alloy. You also need to have your design work with that actuation. So, here is a key reference for this work. This is small font. So, this paper is from IEEE Transactions on Robotics. This is volume 29, 2013 February. So, this is a compact, that is the key feature here. It is compact because of using a compliant mechanism. Otherwise, you could do with a normal rigid body linkage also, and it is a pipe crawling robot external. Here is a problem statement. This is something that Bharat Atomic Research Corporation BARC needed it because they had a bundle of pipes that are closely spaced like this. There are several pipes. So, you can see there is a bundle of pipes, and the spacing between two pipes, this spacing is very narrow. There is a narrow spacing. In fact, it was about 1 centimeter, 10 millimeters or 12 millimeters is what we were told, and we needed something that goes over these pipes to inspect the diameter of the pipes, because when they carry corrosive fluid, it could be eating away the inside of these pipes. So, we need to monitor using some ultrasonic transducers. So, a robot or a pipe crawler has to carry these ultrasonic transducers along the pipe where humans cannot go. It is a hazardous condition where you send the pipe crawler at one end, it will go and then continuously monitor by moving or crawling slowly along the pipe. The challenge here is that if you see this crawler, so let me highlight it. Let us say we have this crawler. This is the one that is supposed to crawl on the pipe like this way, that way. There could be also bends, by the way. A pipe can have bends and so forth. So, it has to move, and the spacing is only that much. So, what we need to have is something that looks like this. In the, if you look at in this direction where the pipes are there, this goes over the pipe. So, the pipe is shown in this black thing here, that is pipe, and we have only about, this is 60 millimeter, this is 90 millimeters, we took 15 millimeters either side. So, the space, radial space that we have is only 15 millimeters. Within this hatched portion, that is our available space, we have to design something that crawls. Okay. It can be tethered because the pipes are there and wires can go over them, but it has to go within that space. You cannot put anything legged features because the space is severely limited here, and this roughness of these pipes is also quite high because these are all used to carry corrosive fluids. So, they are not smooth and so forth. So, it should be able to crawl on those things. That is the problem, that is the problem statement. This is the concept. So, this is like an inchworm motion. So, whenever something becomes green, that means that it is becoming loose. Imagine that like a monkey would climb a tree. So, I have two things here, I will rigidly hold the pipe. Now, when I want to move up, I loosen this, I loosen this and move. So, I loosen and then move and then I hold it, then there is a spring here that would bring me back. So, I start here. So, first both are tight and then I loosen this and there is an actuator that moves it up and then I hold it tight and this loosens and this goes, and that is how it is going to move like we climb a tree, as this animation also shows here. So, the idea of pipe crawler is this inchworm motion. So, that inchworm crawling mode is shown here. There are two rings, basically like what I showed with my hands. There are two rings which are both tightly adhering to the pipe, and then one of them loosens a little bit. So, this one releases the grip on the pipe. So, both the ring 1, so this is ring 1, ring 2 are both are hugging the pipe tightly in the first stage, and then initial stage. First stage, one of them releases and then there is an actuation that moves them as shown by this arrow. So, where what was here, it moved there, that is the second stage. And after that, this will tight, this will ring 1 would tightly adhere to this, and then ring 2 will loosen. When ring 2 will loosen, it will move because there is a stiffness or spring that will make this go. So, now we can see where it was and where it is now. So, it has achieved that much of motion, inchworm motion, where we hold, release, move and move. So, we initially both are holding, one of them releases and moves, then it holds, other one releases, spring will bring it here, and that is how in each cycle you move certain distance. So, in order to hold a pipe and release, we went for a linkage. This is called a Hoberman linkage, which we had seen. There are several revolute joints and there are these angulated members. Here is the thing, if you move these in and out, so which we can see here, as I am moving this in and out. So, you can see this portion is going there outwards. So, it is a expanding circle and a contracting circle. So, this is the mechanism, but putting this on the pipe within that 15 millimeters or 10 millimeters is a challenge, because you cannot make all these joints and we cannot make them really small. Even if you make them, one joint breaking will be a problem and there are a lot of issues. So, we wanted to go for a compliant design here, and in fact, I have a modification of this what you see here. So, what we have here is a circumferentially actuated one. So, there in the previous one, as you can see, we have to move it radially out and in like this. So, how are you going to put the actuator, because there is a pipe in between, there is a pipe as shown with this one here, there is a pipe there. So, you cannot really have any actuator between 2 points to move in and out. So, we wanted to go for something like circumferential actuator. If this is a pipe and we want to go circumferentially. So, we came up with a linkage that actually has a circumferential actuation that will make the some points move in and out, the like previous one. So, they can move like this, okay, or move outwards, radially inwards or outwards, but the actuation is circumferential. So, that is the key thing here, circumferential actuated. So, I have the device here to show you that here is the rigid body linkage. This is not a compliant one, rigid body linkage, and when I apply this actuation circumferentially, that is I am going to rotate it. So, what I am doing here is rotating this circumferentially to move in and out. So, this particular one you can see how the pattern emerges, and this pattern there is a whole paper that is listed on this slide. So, where we can change the pattern, circle if you want, expanding circle, contracting circle, like the Hoberman linkage that I showed. So, here also I can make. Now, what I am doing is my actuation is circumferential like this, I am only rotating this. On the side you see when I do that, it actually completely closes, completely opens. You can hear this sound of several joints, there are several joints here. So, there are total of 1, 2, 3 and there are 8 of them. So, there are about 24 joints in this. So, this is not going to be suitable for miniaturization, because you can see when it hugs the pipe and loses grip, there are all these things that require a lot of space, and 50 millimeter is not going to be, and also there are these additional degrees of freedom that it has, which we can hear or see. So, there are a lot of issues with that. How about a compliant version of that? There is a partially compliant version that is shown here, which I have the device and which you can see on the thing also here. Now, instead of those many joints, what you have are the pin joints only here. So, there are pin joints 1, 2, 3, 4, 5, 6, 7, 8. 8 pin joints instead of 24 pin joints in the previous one, and this actually can go. So, when I am applying the circumferential, I am rotating one with respect to the other, these rings, this actually in a layered structure just like this was. This also a layered structure, there are actually 4 layers here. Now, with the compliant one we reduced it to 2 layers, and by moving it like this we can make this hug the pipe or release the pipe, hug the pipe, release the pipe. So, that is how this is meant to work. Here we can see that in the slide that we have an upper ring and a lower ring, and the spacers are where we have joints. We do not want joints. From 24 joints we reduced it to 8 joints, but we do not want them also. This is still partially compliant mechanism. Is one improvement. We want to go towards a case where there are no joints at all, so that we can make it very compactly with appropriate material for actuation. So, you can see how this gap increases to something bigger and bigger and bigger, and then as you release this grip, it will go from one to the other. So, here it actually, this is the force free configuration, apply force, it makes it, they move to reduce the thing here, they all radially move inwards, all points move more inwards, so you are applying more and more force here. So, it is somewhat like this. Okay. Now, how do you make a fully compliant version? That is what is shown here. So, now we have this ring and there should be another ring, and here is where they are going to be attached. So, when this point moves along the circumferential direction in all these cases, when this point moves circumferential direction, these points will move in the radial direction. So, to see that, imagine that we have circumferential input here. By circumferential, what I mean, circumferential input, what I mean is that we are moving this point along a circle where the center is somewhere here. Here is where the center is, which is this here, we are looking at one of them. So, this point is moving along the circumference, it is like a displacement along a circular arc. When I do that, if I have constrained this to move in a radial direction, that is done with symmetry. We take this ring, take another ring, flip it like a mirror image and put it on top of that like this. So, there are 2 rings here, there is one ring, the other one is mirror image. So, that is why one has a thing like this here and another one has, you have to see that one goes like this, other one comes from underneath in a direction that goes like this. There are 2 things which are mirror images of the other. So, we will have a solid model to see this better. So, when you do that through symmetry, when you do this, this is going to move like that. So, you can see that when you apply the input here, the output in this particular case it is not radially inwards, but radially outwards, it is going like this. So, when this goes like that, this point actually, if I do this, this is actually moving outwards like this. Okay. So, that it will enable us to release the grip on the pipe, it holds and then releases. So, here is the closer look, circumferential input and then radial output. Okay. That is the compliant one, where you can see the beam how it bends. So, to design the shape of the beam, there was a lot of work, because we have to know how much force can be applied, how much we want it to retract, that decides the gripping force that we have, and all of those have to be taken into account, and also high stresses that are experienced at this point, all those things have to be taken into account to design this. And here is how it looks. You can see that individual thing is over here that we saw. There is another one behind, which is the second ring within this, that is going to be attached over here for all 4 of them. It is showing one ring actuator. What is actuation here? Actuation is with shape memory alloy. So, when you have shape memory alloy, you put a wire, this black one that you see from here to here. If you heat it, it is going to contract, that is going to provide the circumferential actuation. Whatever we said that we have to move this along the circumferential direction is done by the shape memory wire. So, we have one wire there, another wire the other side, there is a black one that goes like this. They are going to pull these individual 4 segments, you can have 4, 6, 8, any number. So, gripping pads are shown here. So, any number of them can be done, any number of segment shape memory alloy wire can be put, and that is going to do this. When shape memory alloy contracts, it is going to apply the circumferential actuation. When you cool it, it is going to, the mechanism, since it is deformable, it will pull it back to the original state. So, it can go one more round, because the inchworm motion or a monkey climbing a tree is a cyclic motion. So, it has to come back to the original thing and then do all over again. So, here is the prototype actually, where the SMA wire, 2 rings, you can see what I told about things overlapping. So, one of them is like this, the other one I will do with a different color, it is exactly mirror image of that. Yeah. So, these 2 are attached to one another. So, same thing, one is like this, the other one it goes opposite, they are both welded here. So, they are flipped and put, there are 2 rings here, and which is what I have the device here, what I am going to show this prototype. So, here is where it actually made of spring steel. So, spring steel device where we have this is exactly the diameter or the wire. Okay. So, where there are again 2 layers, ignore the plastic one, that is only to put another actuator later. There are 2 spring steel things here which are attached at the pads, and they are flipped. So, one of them goes one way, the other goes the other way. So, we can see one of them like this, other one goes the other way as the diagram is shown. And you need to have, this is the one that can grip the pipe and release, grip the pipe and release. So, it is a circumferential actuator, actually there is a SMA wire going through this here and then going through here. When the wire contracts relative to the one, the other one wire it attached to one. So, other one will move like this, circumferential actuation, then it will release the grip. Now, when the wire cools, the mechanism since deformed, it will bring it back to the other direction, it actuates and then it comes back, at the time it will come back and grip. So, by having a very compact SMA wire is just a wire, and this whole thing, as you can see, it is not more than 15 millimeters that we wanted, and it can be very long, pipes are long. So, there is one ring, another ring, this can release and grip, other can release and grip, between them we need another actuator and a spring to move it step by step by step. Okay. So, shape memory alloy, it is a smart material, and we need to understand how to work with it, because it is a phase transformation material. So, as you can see in the diagram, temperature versus the load that we are showing. So, it switches between martensitic and austenite phase. So, first when you heat it, it is going to contract, whatever is here it is going to contract, and then when you cool it, it is going to martensite phase, where if you stretch it, it will be in some stretch state and then it will go. This initial, afterward cooling and heating can go back and forth to contract, and then mechanism has to pull, nobody is going to pull it, right. So, if we have shape memory wire that is in some stretched condition, when you heat it, it is going to contract by going to austenite phase. After austenite phase, something has to pull it back. That pulling back is your spring or your compliant mechanism here. SMA wire actuates compliant mechanism when it is heated. When the wire is cooled down again, it will stay there if you do not do anything. It has to be pulled back to the original state. Let me illustrate with a diagram. So, here compliant mechanism is represented like a spring, and so is the shape memory wire as another spring. Both have their own stiffness. Only thing is SMA wire also has the actuation capability. So, what we do in the beginning is to get these two, attach them. When they are attached, they come to some kind of equilibrium. The displacement here and here need not be equal. So, it depends on the relative stiffness of the SMA wire spring and compliant mechanism spring. They will have some equilibrium at room temperature. This is at the room temperature. So, you take one and fix them at some point, now we apply force and bring them together to come to some equilibrium. And after that, so at that point in this particular thing that we have used, you have used, that has 2% strain. Now, when you heat it, what will happen is SMA wire is going to contract. If the spring, that is compliant mechanism, is not there, it would have probably gone up to here, but now it has to pull the mechanism also, it has settled at that point itself. So, what was here now was pulled, it came to some equilibrium with the spring. Now, when you heat it, it went, if the spring were not to be, it would have gone a lot more. Now, it cannot, because it apply force, it settles somewhere. Now, when you cool it, what we want is it has to come back to this position, so that we can repeatedly go heating and cooling. So, we can have this much of actuation. This is our aim, to actuation, repeated actuation, repetitive actuation. So, we had heat it, cool it. So, the mechanism has to have sufficient stiffness to pull it back after cooling, and the actuator should have sufficient force to pull it by that actuated displacement whenever you heat it. So, you have to design the mechanism in accordance with the stiffness shape memory actuator as well as its force capability. So, what we did was SMA wires that we have, we actually did an experiment to see what is the stiffness in the martensite phase and what is the stiffness in the cooling phase, the austenite phase. So, here we saw that stiffness is 26 kilonewton per meter, is 78.48 kilonewton per meter. So, we want to have compliant mechanism stiffness in between these values. So, upper limit is 78 kilonewton per meter and the lower limit is 26 kilonewton per meter. So, here is where compliant mechanism stiffness should be there. So, it should be in between, so that it can go both ways, that is, if it is very stiff, SM actually will not be able to pull it, should be some value. And the cooling phase, if it is again compliant mechanism stiffness is lower than that, it will not be able to pull it back. So, we have to pay this attention to this detail in designing compliant mechanisms. Here is where initial design that we talked about, circumferential, radial, that is more of a functional feature. That is what we have discussed with the design features a lot, design techniques a lot. But now we also need to worry about the strength, that goes without saying, but additional stiffness, a particular value that works with this SMA wire, that was very important in this project. So, when we do that, when we have the SMA wire, these things would move. And in fact, when we started it out, for each of these actuators we had 4 quarters of SMA wire, and all these electrical connections, because this is we are made with spring steel and SMA wire cannot touch this. So, we needed to put some insulation where SMA wire, because we heat it by passing electric current through it. So, we cannot short circuit it because this spring steel. Why do you go for spring steel? If we went for plastic, first of all it is hazardous nuclear environment, plastics may not survive. The other is that they do not have enough stiffness to apply gripping force on the pipe. So, only something like steel or metal will have enough stiffness to apply enough force on the pipe to grip it, because the pipes can be vertical, horizontal, bends and all of that. We need to go for spring steel. With spring steel, when you go, then we have this problem of electrical insulation that needs to be done for SMA actuation. We did all that. When you put 4 segments, any little misalignment in these 4 segments, it will make this mechanism not everything move radially outward, it will also move sideways. So, because it is a compliant mechanism, there are no sliders to ensure that it is moving only in that radial direction. It also can move. Any misalignment, any asymmetry in assembly was causing problems. So, there are a lot of issues that needed to be sorted out, and the stiffness in the other direction, what we call cross axis stiffness, had to be taken care of, so that under these circumstances these pads move only in radial directions upon the SMA actuation. Instead of 4 SMA wires, we ended up using only 2 by putting 2 of them together here, 2 of them together in an arrangement, so that with asymmetry misalignments we kept it to the minimum. Those are all the details that are also explained in the key reference paper that I showed at the beginning. So, now we have ring 1 and ring 2, and in between we have another SMA spring and a bias spring. So, this is the one that if these 2 are gripping tightly, one of them releases, then the actuator will move it down, SMA contracts, this SMA spring here will contract, it will come down, and then this would grip it tightly after moving down. Let us say it has moved here, now at this point it will grip it tightly, then you release it, and these other springs that we have, they will move it here. So, what was here would have moved down. So, this is a gripping release, in between we have linear actuator, translational actuator, and then the spring moving. So, both are gripping, this releases and moves down, and now the actuator will move this down, and now this will grip, this will release, and this will come down. So, you can actually do this step by step. Let me show you one more time. Both are gripping. Now, the bottom one releases. When it releases, we have an actuator that will move it like this. Afterward, this will grip and this will release. When this releases, the spring between them will move it down. So, it had come to another state. That is how it will move one by one like inch-worm motion. That is what we have. These actuators and bias spring here, they also have to be done in the same way that I described. So, one of them should be able to compensate, that is the spring that we have, the bias spring should be movable by the SMA force, and when SMA actuator cools, it should be able, the spring should be able to move it back to the original state, just like what I showed for circumferential actuation also. That is something we have to remember when you use SMA wire or SMA strip or any SMA or Chemery alloy actuators. Inch-worm mode that I just described with my hands, that is here, and that needs to have voltage applied. This is the voltage applied for each of these. So, we have compliant ring A, compliant ring B, and then there is translational actuator in between. So, initially we take compliant ring A, 2 volts is applied, the other things are not there. When you release that, you also are applying the translational actuator after a little while. So, there is a little delay. So, after that this is there, that is 5 volts, and then that comes down. So, at that time the second one, after a little while, the second ring actuates, and then the translational actuator again has a negative voltage to move that back. Here what we have done is, instead of using SMA for translational actuator, we have actually used a DC motor. That is why plus 5 volts and then minus 5 volts reversing the direction. So, it moves like this, moves like that. Instead of SMA, this one is showing where translation actuator is a DC motor, as you will see in the prototype. So, for that we needed a controller, because there are 3 actuations now. So, a controller was built and attached to this pipe crawling device. So, what we have here is this DC motor. So, here what we have, not a SMA 1 now in this prototype, we had done SMA also, but that became difficult and also slow, because SMA has to be heated and then cooled down, and you do not get much motion. The crawling was really small. So, we thought DC motor is good, because holding grip tightly and release, in between the translation actuator would move here. This is a prototype, and here you see it is holding against gravity. So, we have the pipe here, this was supplied by BARC to us, and it is holding by itself, and now when you apply actuation, it just fell down because of gravity, because gravity is there, it lost the grip and fell down. This is one ring, and here is where we have the crawling taking place on a straight pipe. We have the pipe, you can see the thing, it is step 1, and then step 2 when it releases and it has moved. So, this gap has reduced, and then second one, this holds tightly now and this releases. So, this has moved that way, and then this goes on, next cycle it will keep on moving on a straight pipe. Now, we also demonstrated on a bent pipe also. Here is there is a bend in the pipe, and over there also it can negotiate, because it is compact. If it not to be compact, it would not be able to do this. Ideally it will probably need around 120 degrees, even 90 degrees if you want, then you have to make it even more contact to make this actuator. So, to recapitulate the main points here, we have used a circumferentially actuated radial displacement compliant mechanism that is fully compliant. That is something to remember. We started with a rigid body linkage that had 24 joints and made it into a compliant wing that has no joints, entire is single piece. It is an external crawler, there are not too many external crawlers in the literature. It moves on the outside without legs, it is just gripping and moving, it is all very compact. And we also showed how or what we should do when we have SMA actuation, because we have to have the stiffness matching with SMA actuation. So, that mechanism stiffness is in between the two extreme stiffnesses of SMA in its martensite and austenite states. And we used compliant mechanisms in a device that is reasonably sophisticated. It is a robot, a device that crawls on a pipe. Thank you.